All right, guys, Mr. Antonucci here, and in this video, we're going to talk about how to find an indefinite integral using substitution. Now, this is the third video for section 6.5. Now, a lot of the integrals that we went over in a couple of videos ago from that table of basic integrals I gave you, they're not always going to work. But sometimes you can use the method of substitution, which I'm going to show you right here, to find the antiderivatives. So for example, if we have integral of x squared plus 5 cubed times 2x, we can use the substitution that u equals x squared plus 5. Now, the differential of x squared plus 5 is du equals 2x dx. Now we can write that integrand in terms of u and du by substituting u for the x squared plus 5, so that'd be u cubed, and 2x dx is going to be substituted with du. Now we can get the antiderivative with respect to u because we essentially substituted all the x's in terms of u. So this would be the u to the fourth over 4 plus c. But then you want to back substitute and get your answer in terms of x. So it's x squared plus 5 to the fourth over 4 plus c. And again, we can verify that result by differentiating. And you would have to use the chain rule in order to differentiate. So essentially, the method of substitution is based on the chain rule. So just review that real quick. If you remember, the derivative with respect of f of g of x is equal to f prime of g of x times the derivative of g of x. Okay? Now, the chain rule provides a nice template for finding integrals that have that form. So essentially, if you have an integral of the form f of a function's derivative evaluated at another function times the derivative of that inside function, then you can use substitution. So here, this is like the g of x, and this would be like the g prime. Okay, so let's go ahead and check out some examples here. So we want to find the indefinite integrals here using U-substitution. So in the first one, a, since the function is sine of 3x plus 2, that's a composite function. We know the antiderivative of sine x, so we're going to let u equal the inside stuff there. Okay, then the differential du is going to be 3dx. Okay, now notice that there is no 3dx here, but we can adjust for the constant by dividing both sides of the differential equation right here by 3. So you have du over 3 equals dx. And then our integral becomes the integral of sine u du over 3. And then by the properties of integrals, I can factor out that 1/3 and get integral of sine u du. Now the antiderivative of sine is negative cosine, so negative cosine u plus c. Okay. And then back substitute the u, negative 1/3 cosine of 3x plus 2 plus c. And there we are. And again, you can solve or check by differentiation. Now, in the second one, you have x multiplying the composite function square root of x squared plus 1. So here, we're going to let u equal the inside stuff, x squared plus 1. du is equal to 2x dx. And notice you have an x dx here, but not a 2. We can adjust for the constant by multiplying both sides by 1/2. So 1/2 du equals x dx. So this integrand is going to become, or the integral is going to become integral square root u du over 2, which we can rearrange and rewrite as 1/2 integral u to the 1/2 du. I essentially factored out the 1/2 and rewrote the square root as an exponent of 1/2. Now the new exponent is going to be 3/2 multiplied by 2/3, and that's multiplying the 2 that's already there. Alrighty, so the 2's cancel, and you'd have 1/3 times u, which is x squared plus 1, to the 3/2 plus c. Don't forget your plus c. That's very, very important. Okay, now this last one here, e to the x over square root x. Okay, so this one's a little tricky, but if you tried to let u equal the numerator, that's going to be kind of tricky. If you let u, for this one, u equal the square root, because that's what's inside the e to the x function. If you let u equal square root x, then this would be x to the 1/2, and du is equal to 1/2 x to the negative 1/2 dx, which is equal to dx over 2 square root x, if you bring the negative 1/2 exponent to the denominator. Now, we do have a square root of x in the denominator here, but we don't have that 2. So this implies that 2 du is equal to dx over square root x. So this integral would become e to the u times 2 du, all right, which is 2 integral e to the u du, which is 2 e to the u plus c. And then we back substitute to get it in terms of x, e to the square root x, 2 times e to the square root x plus c. All right, so hope that one was helpful to you. Now, substitution is often a good strategy when an integral equals the product of an expression involving a function and its derivative. So we had that in example B and C here. Now, if we move on to the next example, these look a little bit different. And so we may have to get a little bit creative here because sometimes if you pick the incorrect substitution, you'll end up with a more complicated integrand. So the idea behind substitution is to substitute so that you have a simpler integrand. All right, so let's look at part A here. Here, the numerator equals the derivative of the denominator. So we don't actually have a composite function, but if we let u equal e to the x plus 4, then du is going to be e to the x dx, and everything lines up. And so we can substitute and get integral of 1 over u du. Now 1 over u, the antiderivative is natural log absolute value of u plus c, and that's going to be natural log absolute value of e to the x plus 4 plus c. Now, since e to the x is never negative, it's always actually positive, the absolute values are redundant in this case because e to the x plus 4 is never going to be negative for all real numbers. Okay, so we could use parentheses instead of the absolute value symbol there. Okay, it's not wrong to leave the absolute value symbol on there, it's just redundant. Okay, now for part B, notice that the numerator again equals the derivative of the denominator except for a constant factor. So we'll try u equals 4x cubed minus 1, then du equals 12x squared dx. But the problem is you only have 5x squared dx. So what we could do is multiply both sides of the differentials by 5/12. Okay, if I multiply by 5/12 on both sides, The 12s here are going to cancel, leaving a 5 so that things line up. Okay, so you'd have 5/12 du equals 5x squared dx. Now our integral is going to become the integral. The denominator is u. The 5x squared is substituted with 5/12 du. So if we just clean this up a little bit, you'd have 5/12 integral 1 over u du, which is 5/12 integral, or excuse me, 5/12 natural log absolute value of u plus c. So 5/12 natural log absolute value 4x cubed minus 1 plus c there. So in these two examples, the integrands have a numerator that is the derivative of the denominator, and you might have to adjust for a constant, but that gives us the following formula. If you have the integral of g prime over g, then it's going to be natural log absolute value of g. So notice that this is the absolute value of g. It's necessary since the domain of the natural logarithmic function is the set of positive real numbers. So like we did here in example A, we knew that e to the x plus 4 is always positive, so the absolute value is not required. Okay, so let's look at these two examples here, and we're going to talk about how to establish an integration formula. So here's where we're actually going to figure out the integral of tangent and the integral of secant. So if we look at tangent, integral of tangent x, tangent you can rewrite as sine x over cosine x. Now, sine and cosine are derivatives of one another, so I can think of this as g prime over g, or u prime over u, where u is cosine x, and du is negative sine x dx. And if you adjust for the constant, multiply both sides by negative, then you would have negative integral du over u, which you can write as negative integral 1 over u du, which is negative natural log absolute value of u plus c, which is negative natural log, what was u? It was cosine x plus c. Okay, so that's how we get that it's equal to that. The other one, if I take the negative natural log absolute value cosine x plus c, by the power property of logs, which says that if I have a to the natural log of x, I can rewrite it as natural log of x to the a power, I can bring this negative, since it's really a negative 1, up as an exponent. Okay. And then since you have a negative 1 exponent, you can write that as natural log 1 over cosine x. And guess what 1 over cosine is? That's secant. So natural log absolute value secant x plus c. Okay. So either way. So we proved those ones. Now we got to prove this last one here, secant x. This one's not as straightforward, but if we multiply the numerator and denominator of secant by secant x plus tangent x over itself. All right. Now you might be thinking, how on earth did you know to do that? And are we supposed to know to do this? No, just showing you how it's done, right? I didn't figure this out. I just saw it in a textbook. So if we distribute to the numerator, you'd have secant squared plus secant x tangent x over secant x plus tangent x dx. Now, the numerator is now the derivative of the denominator, because if u is secant x plus tangent x, then du is derivative of secant plus tangent, plus derivative of tangent, which is secant squared x, which is what we have in the numerator here. So the antiderivative is just going to be natural log absolute value secant x plus tangent x plus c. And that kind of proves the formula there. So one thing you want to be careful with, however, is that when you learn this form of g prime of x over g of x dx equals natural log absolute value g of x, you just want to be careful because sometimes students mistakenly make the antiderivative of every rational expression an expression that involves natural logarithms. So for example, you might see 1 over x squared dx and be like, oh, okay, that's natural log absolute value of x squared plus c. But that's not right because you don't have g prime over g. You would just write it as x to the negative 2 dx, which would give you x to the negative 1 times negative 1 plus c. Okay, so the antiderivative of a rational expression will involve a natural logarithm only if it's at the form g prime over g. Okay, so just wanted to make that clear to you guys. All right, so in this one, we want to find an indefinite integral. So here, we're going to let u equal 4 plus x, then du is equal to dx. And that looks good, except we still have an x here that doesn't get substituted because the 4 plus x, this is going to substitute here. And the dx is going to substitute the dx, but nothing is going to substitute the x that's still there. Well, the trick is take this equation that has a relationship between u and x and solve it for x. So u minus 4 equals x. Now we can substitute everything. This becomes the integral of u minus 4, make sure you put parentheses, square root of u du. All right, so u minus 4. And you might be thinking, well, that all that does is just kind of rearrange it. You still have the same level of complexity. Well, the nice thing is now the square root is just on the u, and I can now distribute the u to the 1/2. So this would be, remember, this is understood to have an exponent of 1. So u to the 3/2 minus 4u to the 1/2 du. Okay, so the new exponent is 5/2. The reciprocal is 2/5 minus new exponent here is 3/2 multiplied by the reciprocal, which would be 2/3, but multiplies that 4, so you'd have 8/3 there, plus c. And then we back substitute. So this would be 2 times u to the 5/2, so 4 plus x to the 5/2 over 5 minus 8 times 4 plus x to the 5/2 over 3 plus c. Okay, now there is another way to do this one if we let u equal the square root of 4x, 4 plus x, excuse me. Then u squared equals 4 plus x, and then x equals u squared minus 4. So that integral becomes x gets substituted with u squared minus 4, and the square root 4 plus x gets substituted with u. Now here we differentiate the u squared, so it'd be 2u times du equals dx. You could differentiate this u here, but then it becomes more complicated with the square root. So the 2u du is going to replace the dx, so 2u du. All right. Now that's all going to be multiplied together, so we could factor out that 2 and distribute the u. This u and this u would make a u squared, and then when they distribute, you would have u to the fourth minus 4u squared du. And then you'd have 2 times u to the fourth would be u to the fifth over 5 minus 4u to the cubed, or u cubed, over 3 plus c. And then this is where we could back substitute what u is. Remember, u was square root 4 plus x. So this would be 2 square root 4 plus x to the fifth over 5 minus 8, because the 2 is going to distribute to both of these. Square root 4 plus x cubed over 3 plus c. Okay, and then since you have square root to the fifth power, that exponent, if you rewrote it as 1/2, would give you 5/2, and over here would give you 3/2. And then you'd be back to what we had right here. All right. So let's look at another one here. We have 2 integrals here. So the first one doesn't look, it looks familiar, but maybe not completely familiar. So this first one may look like the integral of 1 over square root 1 minus x squared, which is equal to the sine inverse, or arcsine, of x plus c. So we can actually do that. If we look at the integrand of 1 over square root 4 minus x squared, it's going to take a little bit of algebra, but we can do that. If you factor a 4 out inside the square root, you would have 1 minus x squared over 4. Okay? Now, since you have multiplication in the radical, you can multiply the factors separately. Well, square root of 4 is just 2. And then this will be 1 minus an x squared over 4, you could write as x over 2 quantity squared. All right. So this looks a lot more like that right there. So here, what we're going to do is we're going to let u equal x over 2, and then du is equal to 1/2 dx. Okay. So the integral becomes the integral of dx over 2 square root 1 minus x over 2 squared. Okay. Now, if I let u equal x over 2, or excuse me, if I let du equal 1/2 dx, that's going to take care of the dx and the 1/2. So du. And then the x over 2 is going to be substituted with u, so this would be 1 minus u squared. Now this is going to be sine inverse of u plus c, which is sine inverse of x over 2 plus c. All right, pretty cool stuff there. I like that one. Now the next one, dx over 9 plus 4x squared, that resembles, okay, the tangent inverse derivative. So the integral of 1 over 1 plus x squared is tangent inverse. So we can actually rewrite the integrand. So let's look at the integrand. So you have 1 over 9 plus 4x squared. You can factor out a 9, so that would be 1 plus 4x squared over 9. And then since 4x squared over 9, I need to write that as something squared. You would have 1 over 9 times 1 plus 2x over 3 squared. Okay. Now I can use that to rewrite my integrand. All right, so if I let u equal 2/3 x and du equals 2/3 dx. So du equal, well, 3 halves du is going to equal dx. All right. So our integral becomes dx over 9 times the quantity 1 plus 2x over 3 squared. All right. Now if I substitute the u, the dx is getting substituted with 3 halves du from right here. And the denominator is 9 times 1 plus u squared. Okay. Now, the 3 halves and the 9 can simplify to 1/6, and we can factor that out. 1/6 integral 1 over 1 plus u squared du. So then we have 1/6 tangent inverse of u plus c, which is equal to 1/6 tangent inverse of 2x over 3 plus c. Boy, oh boy, oh boy. That was a lot of work there, but we did it. All right, guys, that's it for this one. Hope that was helpful. Reach out if you have any questions and take care.